that the homology in degree 0 of Q is morphic as a Poisson algebra to the algebra of I not I. This is essentially what. Now, in our case, A is C infinity of, say, some of M, or M omega is a symplectic manifold. And I is the vanishing ideal of a submanifold, which is quadratropic. So this means that we want to realize this in also taking care of geometry. So we want to do something better. So now we look for, well, this data where now A should be functions on some supermanifold, which contains the original symplectic manifold M as well, the degree 0 part. Then we want the Poisson bracket here also to come from a symplectic structure. So we want this omega. This should be now a graded symplectic manifold, and this should be a symplectic submanifold. Okay, so in particular, since your original manifold was an ordinary manifold, okay, we also could have some fermionic coordinate, but in general, it's an ordinary manifold. In any case, this omega had degree 0, so also this extension must have degree 0. So the degree of this extension omega is 0, and actually the degree, this degree is what is usually called the Gauss number. This is what we call the Gauss number in this class. So you want now a graded symplectic manifold with symplectic form of degree 0, which contains your original symplectic manifold as the submanifold of degree 0. Okay, and you want a function S in this graded symplectic manifold of degree 1, which Poisson commutes with itself, and so then you can define Q this way, and you want HQ0 to be this quotient, but we're now you start with this data. Okay, it's this algebraic construction, but the only thing that you want is Poisson algebra to be the algebra function on a graded symplectic manifold, which contains the original symplectic manifold in degree 0, and that's it. Okay. So I will show you that this is possible, at least in the finite dimensional case. Let me give you some motivation to do this, or some further motivation. So one motivation is that we don't want to take the quotient, I mean the symplectic quotient, because of tropy reduction. We don't even want to take this quotient, which would be too poor. We want to move to a different category, which is the category of differential graded Poisson algebras with this constraint here, and the morphism will be chain map. Morphism of the differential graded Poisson algebras, right? So that's the correct context. But one further motivation for this is quantization. And somehow the idea is that, well, suppose that things are nice enough. So this M is some symplectic manifold. So suppose that you are able to quantize this to some graded vector space. For example, by geometry, some sort of geometric quantization, or for example, suppose that M is a cotangent bundle, and I here just take functions on the base. This is a simple situation. Now here you have some function s, and you want to quantize it to some operator s hat. And the condition that s Poisson bracket s is equal to 0 immediately implies that the commutator of s with s is 0 up to, well, lowest order in h bar. Okay. Now suppose that you can have this exactly. Okay. So this is not guaranteed. Suppose there may be obstruction in doing this quantization, but if you can do this, then you can consider the homology in degree 0 of this operator, and this would be your physical Hilbert space. Okay, so this gives you a recipe to get the Hilbert space of the coisotropic reduction. Even if the coisotropic reduction might be very singular, this is the prescription. Okay, the point that if the reduction is smooth and you can complete this program, this will give you an Hilbert space associated to the symplectic manifold get by reduction. Otherwise, you take this as a definition. Okay. There is a simplified version of this, which avoids the problem of doing some true quantization, which is deformation quantization. So let me assume that you know what this means. So this means that we want to take now some new algebra where you consider formal power series in the original algebra, and we want to construct an associative product of the form the original pointwise product plus epsilon, the original Poisson bracket plus corrections, but we want it to be associative. And in addition, okay, some further property, we want like the unit functions to be still a unit, and we want these actually to be constructed in terms of bidifferential operators, but essentially this is the important thing, that it is associative. And then we look for some element omega of the form s plus correction. So I can take epsilon plus 1, epsilon squared s2, and so on, such that omega star omega is equal to 0. Okay? And then we look for the homology of omega commutator, star commutator. Okay, so this would be, well, no. So this would be the correct kind. We define this to be the deformation quantization of the reduction. Okay? This is the analog of that. And from here you see actually what is the problem. So compute omega squared when you write things this way. So first thing you see that s squared is 0 because s is odd. Okay? You would have s squared, okay, but this is 0 because s is odd. Then at order epsilon you only have the you have this Poisson bracket, so you have epsilon s Poisson bracket s, but this is 0 because this is our classical condition. And then we go to order epsilon squared. So at order epsilon squared there are some things that can happen. So one thing is this bracket here. This bracket here. Okay, so it's S bracket with S1 coming from here. And suppose, let me call the next correction B2. Right? And then there is a term here, which is B2 SS. So I think probably 2. Okay, and then you have to go on, right? Now, you might say, okay, I don't put a correction, I just use S, right? Then this is 0, this is 0, but the problem that B2 S applied to SS might not be 0, okay? So what you do here, however, is to say that, well, actually, I could look for some S1 that kills this term. Now, 1 interesting thing is that out of this equation, you can actually see that S Poisson bracket with B2 of SS is 0. This is always true. Now what you do is that, okay, this means that this is closed in the classical cohomology, but you want to write it as something which is exact. Okay? So if it's possible, then you can find S1, and this works up to the next order, and then you can continue. So it happens that if the cohomology with respect to the Poisson bracket with S is 0 in this degree, so what is this degree? So S is degree 1, so I think this becomes degree 2, Poisson bracket 0. So if the second positive cohomology is 0, these always work. You can keep finding corrections. Okay? So if this second positive cohomology is not 0, then well, this program might break. Okay? So actually H2 not being 0 signals an anomaly in the theory, in this language. It is also related to the other anomalies, but in some non-trivial way. Okay, so now let me show constructively why we can have this VFB, and let me start with a very, very simple case, and then we'll use this to generalize. So suppose that you start with some symplectic manifold, and suppose that you have a function, just one single function. Suppose that 0 is a regular value, and define C to be the pre-image of 0. Okay, so, well, saying that 0 is a regular value means that this pre-image is a submanifold. Okay. And it's automatically quasotropic. Okay, the reason is that the vanishing ideal, so the vanishing idea in this case is the ideal generated by the function phi, and the Poisson bracket of phi with itself is obviously 0. So, I mean, here everything they use is okay, so Poisson bracket is antisymmetric, so phi is a function, so this is so this is automatically quasotropic. Okay. Okay, so more explicitly, the vanishing ideal consists of function of the form f times phi, where f is any possible function. Okay. And then, let me recall you the definition of the normalizer, or the idealizer. This consists of functions of n. Okay, it should be function with the property, so abstractly it should be function with the property that when you take the bracket with the vanishing ideal, you stay inside the vanishing ideal. Now, it's enough to check what happens if I take the bracket with the generator phi because of the Lamnis identity. If I multiply phi by f, right, then well, I also determine whether I take phi out, but this is automatically in the ideal. Okay, so the better situation could be when you compute really the bracket between the function g with phi. Okay? And you want this to be in the ideal. Okay? So actually this now becomes if and only if. So that means that there is some function f such that the Poisson bracket of g with phi is of the form f times phi. Okay? This is a more explicit way of writing down this condition. Okay? So these are functions with the property that when you take the Poisson bracket with the constraint, you get something proportional to the constraint. Okay, how do you resolve this cohomologically? essentially, well, what we are looking for is n mod I, right? And we want to see this as a homology. So the idea that we should find Q in such a way that n is the kernel of Q and I is the image of Q in degree 0. Okay, so this is what we are looking for. And okay, so you see here what happens. So for example, Q applied to something in degree -1 should produce these elements, right? And well, and this should be the kernel of Q going 1 degree higher. So the idea is now that we add a generator in the algebra. Let me call it C of degree +1. And I say that Q applied to a function G must be, well, phi bracket G times C. Okay. Now, out of this, you see that Q of G is equal to 0 if and only if the bracket of phi with G is 0. And, if this happens, then G is certainly in and C. Okay, for this capital. Okay, it's a bit stronger than this condition, right? But we are already on the correct way. So in other words, so what I want to construct is my algebra A, and what I'm saying that in degree 1, this is my original algebra multiplied by the generator C. Okay. The other thing I need is another generator that I call B of degree -1 that I need to generate this ideal. So this is very easy. I just say that Q applied to the generator B in degree -1 has to produce something in degree 0, and I decide to put this phi. Okay. So now you see that, okay, I define now the degree -1 part of my algebra as C infinity n times B, and here you see exactly that the image of Q, so I'll say Q applied to A in degree -1 is exactly the vanishing ideal. Okay. Now, I didn't tell you what the algebra in degree 0 is. But you can conclude it immediately because I've just added these two generators. So, the algebra in degree 0, well, should be your original algebra, it's infinity of n. But this is not enough because, right, you have these two generators, and I don't want only to construct a complex. I really want to construct an algebra, so I can multiply the two generators. And since one is degree +1 and the other one is degree -1, if I multiply them together, I get something in degree 0. So there is another summand in degree 0, which is functions times B. Okay. So now I have to be more careful when I compute the kernel of Q in degree 0. I have to apply to something in here. Okay. So let's compute Q applied to computation. So some function G plus some other function F times BC. Now Q of G is the bracket phi G times C. And then I have to apply Q here. I want Q to be a derivation, so I can use the Leibniz rule. So what happens here is that, I think this was, okay. So what I can do, so I can apply Q to F. This would be the Poisson bracket of phi with F times C, right? But then I already have one C here. So this, I want this square and C square to be 0. These are all variables, right? So this is not there. I can apply Q to B, and this produces phi. So this gives me the term F phi C. And finally, I can apply Q to C, right? But I declare this to be 0. because I don't want to have anything in degree 2. Okay, so this is the result. So, okay, what is the kernel now? So the kernel of Q from A0 to A1, right, consists of pair of functions f and g, such that phi bracket g plus f times phi is equal to 0. And if you notice that, exactly that condition, which means that this kernel is actually isomorphic to NC. Okay? So if you have an element in NC, you already have like the pair G and F. So you could go in that direction. On the other hand, and vice versa, yeah, so something in the kernel. Okay. So far, okay, so we are done. The cohomology, well, almost done. The cohomology in degree 0 of Q is precisely NC mod IC, okay, as an algebra. So notice that, I use the Poisson bracket to define this term here, but I haven't given you the Poisson algebra structure on this calligraphic A. So far it was just some algebra, and Q was a derivation. Okay. Now I have to give you the Poisson bracket on A. Well, this has to extend the Poisson bracket as before, so on functions it's the same as before. So the only thing I have to tell you, well, because of the Leibniz rule of the Poisson bracket, is, well, what are the Poisson bracket involving B and C? And the only non-trivial one is the bracket between B and C. This should be something degree 0, and I declare this to be 1. So in other words, I should think of B and C as conjugate variables. Okay, and the other brackets are 0 because the bracket of 2b's would have degree -2, the bracket of 2c would have degree +2, so they're automatically 0. Okay, now I want to think of these as a manifold, functions on a manifold. So what I do, I define this new manifold curly M, which is my original symplectic manifold, times a cotangent bundle of R shifted by 1. So now my generator C in degree 1 is a coordinate on R shifted by 1, and my generator in degree B is its momentum. So the symplectic form I have here is my original symplectic form plus dB dC. Okay. So now we have a symplectic manifold, and what you have to do, you have to verify that this Q is an inner derivation. So you have to find the Hamiltonian function. So one thing you see immediately that actually you can define S to be C times phi, yes?
By this definition, doesn't C have degree -1 or is concentrated in degree
no, I think no, because R shifted by 1 means that the functions, right, generating degree +1. This is how you define it. Yeah, this is how you, the shift is defined. Yeah. I think so. Okay, but anyway, I want C to be degree 1 and B degree -1. Okay, so claim that the function, the Hamiltonian function of Q is S, is a C times phi, and well, you see it immediately because, okay, well, what you have to check? You have to check what is Q a function, and Q a function is precisely C phi G. What is Q of C? Well, this is automatically 0 because there are too many C's around. And what is Q of B? Well, you can extract phi, and then you're left with the bracket between B and C, which is 1. So Q of B gives you phi. Okay. And the other thing that you can immediately check is that S Poisson bracket S is 0, again by degree, but the reason you have too many C's around. Okay, so we are done. So this is the solution when you have one single constraint. And now you can guess what you have to do if you have several constraints. So now suppose that we have, again, our symplectic manifolds, but now we have several functions, phi 1 up to, say, phi n. And we want to consider C to be the common zero set of these functions. Okay. Equivalently, I'm thinking of phi as a map from n to Rn, and I want 0 to be a regular value. Okay, so this is phi inverse of 0. So this is a submanifold, and I want B to be quasotropic. Well, this happens if and only if there are functions f. Here I want to use the same convention. Lower indices. So there are some function f I j k such that the Poisson bracket phi I phi j is equal to f I j k phi k. Okay, so these are my algebraic data. And now the idea to mimic what we did before is like you introduce C1 up to Cn in degree plus 1, B1 up to Bn in degree minus 1. Or in other words, you consider the manifold N as n cross the tangent bundle of Rn shifted by 1 with these coordinates, B and C. And with symplectic form, the original one plus sum of the I, the Ci. Okay. And then you start with that guess. So let me call it S0. Be the sum of the constraints over this Newton vector. So the good thing is now if you apply, and then you define Q0 to be the Poisson bracket with S0, and the first thing you see is that if you apply Q0 to the variable Bi, you get the constraint phi I, so you generate the ideals, and on the other hand, if you apply Q0 to some function, you get Ci phi I bracket with the function, which tells you that somehow when you're looking for the invariant functions. Okay? The problem is that, well, the Poisson bracket of a 0 with itself might not be 0. Okay? So this is an important condition. You want Q to be a differential. And actually, well, this is actually the problem. Well, let's compute it. So this is Ci phi I, Cj phi j. So I can take the C out. So this becomes Ci j, and then what was the identity? Okay. So this becomes f j k phi k. Okay. So you see that in general this will not be 0 if the f's right are not 0. Okay. But then, well, there is an easy way to solve this. You can introduce S1 to be 1/2 f I j k Ci Cj bk. And you see that, well, this now works nicely because when you compute the bracket between S1 and S0, there is a term, right, that appears from here when you take the bracket between this B and this C, right? Okay, probably nicer to have effects over that. Right, when you take the bracket between this B and this C, you are left with this term, Fi j k Ci Cj. right? And then you're left with this I, which is precisely what you want to get here. So if you put the signs correctly, you can use this to kill that. But of course, there might be other terms, essentially because you will see the bracket of this F here. So the other terms will be something complicated, like there will be some C, I don't know, it's called CR, and then some phi R bracket R S R J K, and then CI CJ BK. Okay? Okay, so, well, if these F's are constants, so if all the F's are constants, F, I, J, K are constant, actually S0 plus S1 solves the master equation. And we are done. Otherwise, you have to continue. You have to now introduce an S2 to kill this term, but then you produce other garbage, and you have to continue. One thing that you notice is that this S0 does not depend on the B variables. This S1 contains one single B variables, and if you think what you need to kill this would be some S2 that contains two B variables. So basically, what you will need is an expansion in the number of B variables.
You mean S0 plus S1 there, right?
S0 plus plus S1. Okay, so what you need is you look for S of the form S0 plus S1 plus S2 and so on, where S0 and S1 are given as there, and where Sk as degree K in the number in the B variables. So this is not the Gauss number, is the polynomial degree in the B variables, such that S bracket S is equal to 0, and the theorem is that this is possible. So this somehow the theorem, well, the heuristic theorem used by Batarin, Fracking, and Wilkowicki, but it's a true theorem proved by Jim Stasher. Okay, so essentially what you do is you can, essentially by cohomological reason, you can show that you can always kill the new garbage by adding terms. I presented it now in the terms of constraints. What Stasher proved was something more. You might have, I proved it for independent constraints. What Stasher proved was that suppose that you are able to give your submanifold in terms of constraints, but with relations with each other, and then the theorem still holds. What happens for a quadratropic submanifold that cannot be given in terms of global constraints? The theorem is still true due to Florian Schatz. So the theorem is that there exists a graded symplectic manifold containing m in degree 0, such that the function s of degree 1 with Poisson commutes with itself. And then the other thing you have to check is not only that, of course, you can extend by garbage and kill everything, but that the cohomology is the correct one, so that the cohomology degree 0 is precisely the quotient we are looking for. Yes?
Could you give some examples of theories where you have to go higher than
For gravity?
Is this the structure contents of functions?
Yes. Another examples which more manageable, but at least topological theory called the Poisson-Sigma model. That's another example where you have to continue. Yes?
So, but locally the picture is always of constraints, and isn't Florian Schatz's paper like a localization of that, or?
I mean, it's, yeah. Okay, so this is okay. So, okay, so this is the final outcome, and well, this is what is called the BFE. Okay, so now, before removing the F and going to the BV construction, I want to make a short digression on the differential gradient symplectic manifolds because, well, this is one example, and we'll need also other degrees. So DG symplectic manifold is a triple M omega Q, where omega is a graded manifold. So by this I mean a super manifold, which means that there is a parity, but with some additional grading, as also Studo was explaining, which often is just a grading in integers, and such that the parity is a reduction modulo 2 of the grading, but that means the other grading could be independent. Then Q is a odd vector field of degree +1, satisfying Q bracket Q equal to 0. So this is what is called the homological vector field. Omega is a symplectic form of some degree, say n, and parity equal to n mod 2. In this case, I want to impose this condition. And finally, I want the Lie derivative of omega with respect to q to be 0. This is the compatibility condition. Okay, so the BFE case that here is when n is equal to 0. Okay. Now, we say that we have a DG Hamiltonian manifold if Q is the Poisson bracket with some function S. So those plus this additional condition. Equivalently, this means the contraction of Q with omega is the differential of S. And now, by degree reason, you see that the degree of S is n plus 1. Okay. Now, one thing that, one remark is that if S has Poisson bracket with itself equal to 0, and this is always a non-trivial condition, right? And actually, yeah, it's actually the parity. You will see that the parity of S is n plus 1 mod 2. So by the parity of omega and the parity of S, you see that this condition is always non-trivial. Okay. So if this condition is satisfied, then Q bracket Q is automatically equal to 0. So you can impose this stronger condition. And particularly in the Hamiltonian manifold, you impose this condition. Okay. Well, the question is whether you can go backward from this condition. You can imply this. This happens in some degrees. So, let me make a short digression on degrees. I mean, here the degree doesn't have to be integers. It could be something else. But the important thing is that the degree of omega is an integer.
How do you have the parity then?
Well, n mod 2. N is an integer. Oh. That's why it's important that it is an integer. Okay. So notice that, okay, what is the degree of S bracket S? Well, S is a function of the degree n plus 1, so we have to add the degrees. So this becomes 2 times n plus 1. But then you have to take the Poisson bracket. the symplectic form at degree plus n, so the Poisson bracket lowers the degree by n. Okay? So to subtract n. So this is a function of degree n plus 2. On the other hand, the condition q bracket q equal to 0 implies that S Poisson bracket with itself is a constant function. It's almost true, but it's a constant function. Now, you see that the only problem you have is when n is equal to minus 2. Okay? So for n different from minus 2, q bracket q equal to 0 is equivalent to S bracket S equal to 0. The reason is that 0 is like the only constant function of non-zero degree is a 0 function. So degree different from minus 2, you're done. Okay, the other thing is, well, now let's be more careful with degrees. So let me denote by E, the so-called graded Euler vector field. So this is the way, well, when you define a graded manifold means that I have this vector field. So what is this vector field? So this is an even vector field of degree 0, such that an object has degree k, or if and only if, so an object phi, sorry, an object psi has degree k, if and only if the rederivative of this object with respect to E is chi psi. So you can compute the rederivative with respect to E, and you can let it act on function, differential forms, vector fields, tensor fields, whatever, right? And you say that that object has degree k if it's an eigen, well, if its eigenvalues is k. Okay? Now, in coordinates, assuming that you have local coordinates xi with a specified degree, it is E is the sum over I, degree of xi, times xi times the partial derivative of xi. Okay? Means the derivative of coordinate should give the degree, so yes, locally should have this form. That's why it's called Euler vector field. Okay? But it's Euler vector field, well, weighted by the degrees. Okay, so now well, some pleasant things happen. So first, we know that omega has degree n, so it means that the rederivative of omega is n omega. On the other hand, since omega is closed, this is just d iota e omega. And the other thing we know is that q has degree 1, so this means that the bracket of E with q is q. These are the derivative acting vector fields. Okay, so now let's compute the derivative of the contraction of q with omega. Okay? So on the one hand, this is something of degree n plus 1. So this is n plus 1 times iota q omega. On the other hand, I can use Cartan calculus. So I can try to so yeah, I can write this as iota e d iota q omega plus d iota e iota q omega. Okay. Now this is the derivative of omega with respect to q, because omega is closed, and this is 0 by assumption. So you see that we have this relation between iota q omega and the differential of this function. So if n is different from -1, we can divide, and we get that iota q omega is 1 over n plus 1 differential of iota e iota q omega. Okay? Which means that q is automatically Hamiltonian, and we can define S as 1 over n plus 1 iota e iota q omega. Okay, so we can recover S from Q, okay, under this assumption. Okay, so the bad cases are n equal to -1 and n equal to -2. So the case n equal to -2 never appears in physics. The case n equal to -1 does. It's precisely the case of the D. So this is the case where S is not completely determined by Q. Sorry, completely is not automatically, does not automatically satisfy the master equation. So you need something more, which is some physical condition. Okay, so I think I'm done with this. Okay. Okay, maybe I can give you examples. So let me give you a very, very simple example. Actually, maybe let's do here. So in the billion case, we saw that our manifold was sigma given by 1 forms on sigma plus d minus 2 form on sigma, right? And C was the common zero set of these JC functions, where JC was integral of C to D. Okay. So here, okay, this is an infinite dimensional generalization, so we cannot really use the theorem, but actually we can find the solution directly. So you might really think of, remember, right, we were looking for S of the form Ci phi I, where this, the phi I are the constraints. Well, here the constraints are the size of B equal to 0. So you might think of this integral really as a generalization of this formula. The only thing that now we have to promote, here we wanted the Ci right, to have degree plus 1. So we have to start from this classical construction where this C was a variable of degree 0. Now we have to promote it to have degree plus 1. So that means we have like this curly space, right, which will be our DFT space, which now has not only like well, the 1 form and the D minus 2 form, right, but those are the C variables. So remember, the C variables were 0 forms, okay? But now we want them to have degree plus 1. And then we have to add the momenta in degree minus 1. This will be the B variables. And okay, the B variables should be paired, right? So we want the symplectic form to be, well, delta B delta A plus delta B delta C, integrated over C. So C is a 0 form, so B must be a top form, which means D minus 1 form. Okay? So this is it. So now, well, I declare C to be integral of C dB over sigma with this new grading. So this is a function of degree 1. And you immediately see that S bracket S is equal to 0. Okay. We can immediately extend this to Young-Mills. Okay, you should do the exercise starting from Young-Mills in the bulk, but I can tell you the answer. So maybe let's just put colors. So Young-Mills, so here everything is some the algebra. And well, you can imagine that the constraints will be actually, well, some covariant derivative will appear. So you will need this term here and also here. But this now will be only the C0 part. Because like essentially here S bracket S equal to 0 essentially because C bracket C was too much. So then you have to correct. So the correct solution will be CdB over sigma. This is our S0, a covariant derivative, and then it will be a term of the form B C bracket C, which is S1. And this is enough. And well, probably you know these essentially, probably you wouldn't call it DFT. In this special case is what you would call BRST. Okay, and this S bracket S is equal to 0. Okay. And if you check what this S does, you see then, well, when you apply Q to B, you get the AB equal to 0. So generate this ideal, you generate the AB equal to 0, and then you mod out essentially by gauge transformation. This is the reduction you get. You see here, well, for example, if you apply Q to, say, to B, gives you, Q to A means that you take the derivative with respect to B, so by integrating by pi you get covariant derivative of C, which is the gauge transformation for A, and so on. Okay, so I think this is it. So now I should start with the BV formalism, but probably, I don't know, makes sense to stop here, see if there are questions. So the idea is that, like just announced, the BV formalism will be this, with n equal to -1, and its application will be to make sense of the functional integral when there are symmetries. And one thing we'll see is how to connect the BV formalism in the bulk with the BVFE formalism in the boundary. Okay? But we'll do everything tomorrow. Okay, so if you have some general questions. Yeah.
So this difference between the Young means and the Billian case is the analogous in the when I do basic Fadel-Popov quantization.
Yes.
And you have to loss.
Yeah, but this is, well, but Fadel-Popov will be related to this case in the bulk. This is the boundary version. Yeah.
And they are related.
Yeah, they're related. Yeah.
Right. So when you said that there is this H2, when H2 you cannot solve the constraint.
Yes.
And
This is exactly well, the H2 on the boundary is related to H1 in the bulk, which is precisely where the anomaly is.
So this is an anomaly for a gauge symmetry.
Yes.
It means that the theory is consistent.
Yes.
Okay.
Yes. We have several ways to see the theory is inconsistent. The way you see it on the boundary, that you cannot, you can also get the VFV action. I think this case is very easy. You stop at the B and B. But the anomaly on the boundary is the fact that you cannot quantize in a consistent way. You cannot quantize this as to some operator that's first to 0. So that's how you see the anomaly on the boundary. In the bulk, you see the anomaly in a different way. That essentially what I said tomorrow, there is a simplified version of this problem, which is a classical master equation, which is precisely differential greatest symplectic geometry to the degree -1. But actually, to solve this problem, you did more, what is called the quantum master equation. And the idea is that you first find the solution of the classical master equation, then try to extend it to solution of the quantum master equation. And again, there can be obstruction to that. In this case, they lie in H1. And so if it's not possible, this is another way to see the anomaly. And this is really related to the usual anomalies.
And this is, maybe I lost it when you said it, but this H2 cohomology group with respect to the differentiation of S?
Yes, this is a cohomology group of a complexity operator.
In which coefficient it's valid in what group? It's an R or discrete group?
Yes, these are functions on the space of boundary fields. And you have the BRST operator acting on these fields. This is homology for this BRST operator.
Is there anything like this for string theory, maybe?
Like that?
For string theory, is there similar arguments like to say for bosonic string?
Yes, if you treat string theory as a Lagrangian field theory, that's like Fadel-Popov action, for example, or
For string field theory, one can, it only makes sense for in 26, like.
String field theory is a theory that describes like the expectation values on like manifold surfaces with boundary, right? And it is also recasted in terms of formalism. Right.
Yeah, no, I was like, because one can see also the fact that one is 26 dimensional on a target, like as a conformal anomaly. some kind of gauge anomaly.
Yes.
I was wondering if one can see.
Yeah,
that.
these anomalies appear in the sense that you cannot define what is called the Bivy-Laplacian in a consistent way, in such a way that S satisfies the quantum master equation. Yeah. We haven't talked about it yet, but that's it.
Yeah, so in the case of Maxwell theory, right?
Yes.
So we say that our basic functions was just omega 1 plus omega d minus 2.
Yes.
Right? But like Maxwell theory, the space of function is, if I'm considering like the standard formalism,
Yes.
it's just gauge connection, right? Not really.
No, it's well, the symplectic manifold is gauge connection and electric field.
I'm thinking about the second formalism, right? The one in which I have only the action dr.
Yeah, but still, you get a symplectic manifold
Yes.
on the boundary.
Yes.
And, I mean, the connection is not enough. It's just one of the field. You need those.
Yeah, I was
you need the momenta.
the Church class, right?
No. Okay, so let's see. If you work in the usual setting, in the usual formulation of electromagnetism, you have said, let me call it the vector potential, A, which is actually a connection, and the electric field. Now I will treat them both as vector. So this setting is better to think also of the connection as a vector field. Anyway, you can use the metric to transform the one form into, right? So on the bound, now where it is on the boundary, and the symplectic form in this case is the integral over the boundary of delta A vector product delta E, and then you take the volume form. You need some underlying metric, Lorentzian, or depending on what you want to do. So this will give you a volume form on the boundary, and you treat the vector potential and the electric field as vector field, and you can compute the inner product using the metric. This is the symplectic structure, and the coisotropic submanifold in this formalism is divergence of E equal to 0. Now the relation, what I was saying, that of course over sigma you have the metric, well, this is the restriction of the metric to sigma, and how do you relate the thing? So, well, what I called A should be a one form, right? So, okay, you related them using the metric. In which direction? I think this, if you write it this way, you have to use G inverse. Right? You transform a vector field into one form using the metric. And what is B? B is the contraction of the electric field with the volume form. So this is why this is a top form minus 1. So and then you get exactly what I was saying. So of course, the physical variables are the vector potential. Well, vector potential physical up to the gauge transformation. You check here when you take this quotient.
Yeah, no,
and the electric field.
my confusion was more about the fact that the space of fields is not really omega 1, right? But it's gauge connections.
Oh, okay. Well, I was assuming that we have a trivial line bound.
Yeah, right.
No, of course, yeah. Of course, you can extend this to the non-trivial.
Also, if I have non-trivial stuff,
sure.
right? But then in that case, because I mean, at a certain point we derived the gauge redundancy, basically, right? So this shift by infinitesimal derivatives, right? Yeah. So if I put like one connection there, then what kind of gauge transformation do I see?
So here I was only looking at the infinitesimal gauge transformation. So okay, in general case, so this will not be omega 1 tensor G, right? It will be connection, one forms. And what I need to put here is omega 0 are actually section of the adjoint bundle. and they generate infinitesimal gauge transformation. So I'm not looking at the whole group.
Okay.
Yeah.
So
That's the
one,
data and information you have to put in separately.
Okay.
It's only the infinitesimal part. You only see the algebra.
okay. 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 Thank you.
More questions? Okay, then we can stop here. Now I think there is a question, but with other people, right? Jennifer?